Okay, I wanted to talk a little bit more about the concept of weight and how it relates back to mass. Okay, so one of the formulas that we have from physics relates the force of gravity. Okay, so basically the idea is if you have two objects, all right, you can find the force of gravity between them, the force that's attracting these two objects together, in terms of this formula. All right, so you may have seen that in physics. If not, here's your first preview of this. All right, so it's some constant g, the universal gravitational constant, and that's shown here expressed in base dimensions. Okay, and then you have mass 1 times mass 2 divided by the separation of the masses. Okay, so let's think about, here's this picture of the Earth. Okay, so the Earth is a circle modeled with a sphere, as a sphere actually, and the radius of that sphere is big. Okay, and in fact, they're talking about that right here with this number, 6.378 times 10 to the 6th meters. Okay, so there's the radius part. Okay, and then you would also need to know the mass of the object under consideration and the mass of the Earth. Okay, so we can estimate the mass of the Earth and we know what the gravitational constant is. And so if we're sitting here on the surface of the Earth, okay, then we are able to come up with a measure of this force. Okay, so the force is going to be the, you take all these numbers, you plug those in, okay, and you're left with, the original formulation says that the mass that you're thinking about, the mass of this object on the Earth, has mass m. All right, so that's plugged in here. And all these numbers crunch down to 9.808 meters per second squared. Okay, so it gives us a simpler version of this universal law of attraction, okay, or law of gravity. Weight is equal to mass times gravity. All right, and so that's the formula that we had used in the part 1 video, and this is where it comes from. Okay, so the next thing I want to do is show you where some of the confusion starts. Okay, we take this formula, weight is equal to mass times gravity, and we start applying it. Okay, so let's say that we have two masses and that they're located on the Earth. Okay, so we know the gravitational constant of the Earth is given by these two numbers. Okay, so I'm looking at this, and the source of the confusion comes from the pound mass part in the English units. In the SI system, things are pretty straightforward because you have W is equal to mg. Well, m in this case is 1 kilogram, okay, the standard unit for mass in the SI system. And then we multiply by g. G is 9.81 meters per second squared. So that gives us a weight of 9.81 newtons. Okay? So really straightforward, you just plug it in. So I think part of the confusion factor that students have when they're first starting to use pound mass using engineering formulas and physics is the following. Let's take 1 pound mass, and what we know is 1 pound mass will exert 1 pound force. Okay, so that's if we're on the Earth. Okay, so if that's the case, then we take a look at this formula. Weight is equal to mass times gravity. And we realize, wow, if I plug this 32.2 in and the mass is 1 pound mass, then I'm going to get the wrong answer. I'm going to get 32.2 pound force. Okay, and so Hagen offers up the fix. He says, okay, if you're going to use pound mass, you have to modify this formula for gravity and weight. Okay, so the modification is to first divide by GC, okay, where GC is the gravitational constant of Earth, okay, and that's part of the definition of pound mass, okay. We'll talk about that more in just a second, why it's part of the definition. Okay, so if that's what we did, then if I plug in 1 pound, the 1 for the 1 pound mass, and then I divide by 32.2, and then I multiply by G, which is also 32.2, these cancel, and I get the answer 1 pound force. Okay. Well, if I'm you and I'm watching that, I think, well, that was kind of silly. I just multiplied and divided by the same number. What's the point, Dr. Thompson? That's probably what you're telling or thinking to yourself. Okay, so let's see what the point would be by moving the mass to the moon. Okay? All right, so if we move the mass to the moon, these formulas work out somewhat the same. They're the same types of application. Let me hide this. I need to erase this. I'm sorry. Hang on. All right. We are now on the moon. Okay? So these gravitational constants are not the same. All right, so we can go back up and look from the previous videos. We know on the moon it's 1.62 and 5.31. .62, 5.31. This is feet per second squared. This is meters per second squared. Okay, and so we're wondering what the weight would be. Okay, so if we do that, we take W is equal to M times G in the metric system. Everything works good because the mass is already in kilograms. That's already a standard unit. So we do 1 times 1.62 and we get 1.62 newtons. Easy enough. It's easy under the SI system. Okay, but if we're going to do this under the English system, because we're not using a standard unit, the approach of Hagen is we need to use the modified formula for weight. Okay, so the modified formula for weight we just talked about was mass over GC times G. Okay, so GC comes from the gravitational constant of the Earth, and that's part of the definitions. When you look at a definition of a slug, it's related back to the gravitational constant of the Earth. Okay, so if I plug in 1 pound mass, all right, and then I divide by the gravitational constant of the Earth, which is 32.2, and then I multiply by 5.31. When I do that calculation, then I get the weight. Okay. You plug in this calculation and you get 0.164 pound force. Okay. All right, so to me, this process of having a different formula, all right, so right here, we had a different formula that had to be used when we applied pound mass into the gravity or the weight equation. Okay, so another concept that you could use that would fix this problem is to take the idea that the formulas are going to be the same. Weight is mass times gravity. However, when you use mass, it needs to be a standard unit. The standard unit for mass is slugs. Okay? it turns out that the definition of a slug is that one slug is 32.2 pound mass. Okay, so if you simply do this unit conversion, you're good, okay, because you can always convert pound mass to slugs and apply the formula. So if I did that, I would take the 1 pound, I would divide by 32.2. Look, that's what I did right here. Okay, and then I'd multiply by gravity, and everything would take care of itself. All right, so I mentioned that because in my mind, it's harder to reconcile using two different formulas. Okay, in one case, I use m over gc times g. In one case, I used m times g. Why did I have to do different units or different formulas? And it all comes down to what is the standard unit. You need to make sure you use the standard unit when you plug into a formula. Okay, so hopefully that will make some sense, and we'll do some practice problems to work that into our memory banks.